I'm going to show you how to design PID controller for a given process. Okay, so if suppose we know the transfer function of a process, which is this. So you can see this is a second order process, right? So if we know the process transfer function, and then for GT transmission is one, we don't have anything. Valve is one, and then maybe we have disturbance, okay, to the process. So this disturbance will come before GP. Okay, so now we need to design a PID. So suppose first thing is to do the open loop response. Okay, and we do a step change, and then approximate this second order function to a first order. Okay, so let me start with the beginning. So we start a new let me start new blank model. Okay, library function. We look for transfer function, search. So we have transfer function, just drag it here. It's a bit slow. Okay, and then we need a step function. Okay, right click, add a scope. Yeah, this is faster. So now, okay, so we have transfer function, set point. Okay, uh, our transfer function given is this is this. So we have second order transfer function. So we can make it, right? So if you want to just write it this in this way, so it becomes either you can have two first order in series, or you can make it like this. So this will become 2s square plus 3s plus 1 and 2. So what we have, 2s square plus 3s plus 1. So and then here we have 2. Okay, so now that's it, and make it big. So here we have, so this is open loop, no control, right? We are not measuring where there's no controller, so this is open loop. A step change, okay, we can have step time at 0, and from 0 to 1, okay, as or 0 to 2, whatever we can do. So if we run this one, okay, so now we can see this is the response. So this is the second order process real. Okay, you can see here little bit of time delay. If you zoom it, you can see little bit of time delay here. So now this, using this graph, you need to come up with first order time delay model. Okay, so using like 63.2% method, or fractional incomplete method, there is a procedure. So for example, 63, this is the steady state value 2, and then you need to know like 163.2% of 2, so 1 point something, and what is the time. So using this, you can get the first order process. Okay, and then it is then you will use this as transfer function for the control. Okay, so now suppose I'm just doing a number. And gain you will get, right? Suppose I got the gain 1.5, and then time constant 2.2 s plus 1. I'm just assuming a value. Okay, so this is approximated first order model for the process, and now we will use this one for the control, for the controller design. Okay, so okay, let's now I can change this 2.2 s plus 1. So I can change this become first order 1.5. This is just I'm okay. Okay, this one close. So this is my approximated function first order. Now I will use controller now. Okay, so what we need now it will be closed loop. So response, and then here we need PID. Okay, so PID, and then before that we need a sum block. So set point, and then we have PID. We will be designing PID controller using the cycling method, right? So cycling method, initially you will use only, so this one should be plus minus, only KC. So we have PID controller, then this one we need to make like this. So right, so this is the output is measured, and then controller will take the action. Now we will do the cycling. Cycling means what? We will have the set point. Okay, this is the change in set point 0 to 1, and then PID controller only KC. Okay, now KC you should have an idea from the process using the root scalability criteria. Then what should be the range of KC? Okay, here I will use some random values. Okay, let's see. So proportional integral, sorry, only proportional controller we are using. So you can see this is only P value. Okay, KC, this is KC 4 I used. Now I run this one. Okay, so from the set point 0 to 1, this is going from 0 to 0.85. So we have offset, right? So what we need to do, we will be increasing the value of KC until we get the oscillation, continuous oscillation. Okay, so actually I was not able to get the cycling in that, I had the random values. So suppose this is a process diagram. This is the process, okay, transfer function for the process 0.5. So I keep it as it is. It's not approximated model. This is the process, and then we suppose we have valve, and valve has first order transfer function, and this is PID, and then we have also in this case we have disturbances too. Okay, so now PID, what we need to do for cycling, we need to only run the proportional controller. Okay, so proportional controller, suppose I did make KC10. Okay, I need to make it 0. So KC10, and then run this one and see the response. Okay, as it is oscillating, but it is oscillation is dying. It's oscillating, oscillation stops. So what we are looking for? We are looking for something like this. Like the amplitude should be constant. Okay. So what we can do? We can increase the tau I. Sorry, KC. Okay, make it 15, 16, something like this. Run it. Now you can see oscillation increases, but the amplitude is decreasing. So we need to increase further. Okay, 16, 17. So this is trial and error. You need to keep changing KC value until you see. Yeah, you can see almost it is little bit decreasing. So maybe you need to increase little bit more. Okay, 17.32 whatever 4. Suppose I did. Now you can see almost. So this one little bit increasing here. It means we need to decrease a little bit. So for a process we can fine tune. So this is the value of like Kc at which it becomes continuous oscillation. So this is ultimate gain Kcu. Okay, and the period will be, okay. Let's make it 7.3, and the Pu ultimate period is the time difference. On x-axis we have time, so time difference of two peaks, that's Pu. So Kcu at which this Kc value of at which this becomes oscillatory. So for example, for this process I have 17.3, and then you find the Pu. Okay, the time difference of two peak, that's ultimate period. So using Kcu and Pu, Kcu and Pu, see the table for Ziegler-Nicholas and TL method. There is Kc value, tau I value. For Pi, then we have PID, right? Tau I and tau D. This is based on Kcu and Pu. Then run the process for this. Okay. For example, I will run it for. So in this case, this is Kc. This is integral gain. Integral gain. So this will be like this is ultimate gain, right? So ultimate gain times maybe 0.45, and then integral. So this is Kc. So Kc is 0.5 times 17.3. Okay, and then Kc, this is Kc divided by tau I. Tau I. Okay, suppose we have tau I equal 10. So this is the gain, integral gain. This is Kc divided by tau I. Okay, so now we run for this and see the response. So okay, it is reaching a steady state. From 0 to 2 we have step change of 2, so it is going to 0 to 2. Okay, oscillation is there, our shoot is there, and so on. So based on the values you will compare, you will run for each and compare the performance. Uh, so if you want to decrease the oscillation, okay, what we need to decrease the kc kc and increase the tau I. Okay, so suppose I increase the tau I by 1.5 and decrease this by 1.3. Okay, I'm decreasing the kc and increasing the tau I. I expect that I should get less oscillation. Yes, so it is reaching a steady state faster. For example, extreme case, I can show you by increasing the tau I too much. Okay, 5 times. Okay, so it becomes a little bit unstable. So basically, you increase the tau I, it will be less oscillatory and slower. Okay, so based on the values you are getting for PID, for TL and Ziegler, you can compare the performance, and then final step is to see, like, compare the controller performance based on TL and ZN, and then come up with the, you do the fine tuning, change KC, change tau D to see the response, how we can get the better response. Okay, uh, similarly also if you want to see the difference, see how controller, how it's acting when we have change in disturbance, we have disturbance, so you can make the set point change 0. So now we analyze only when we have disturbance, so you need a step change in disturbance. Okay, so this one I make it 0 to 1, so I want to see if there is disturbance here. This is inlet, like coming to the process, right? Some variable to the inlet, how controller acts. So you can see the initially it was at 0, right? Means there is no deviation, she said, and then it goes up and controller is trying to control with some oscillation and is reaching the set point, it is reaching back to the set point. So this is not ideal scenario. Okay, ideally we want something like this. If it is here and goes up and then comes back to the this. So depending on your controller values P, Kc, tau I, you will get this response. Okay, so I think this should help. Well, let's stop here. Okay.